In this video, we're going to talk about simple pendulum. So what is a simple pendulum? So we have a particle-like object. It's a bob that has a mass m. So here I have mass m that is attached by a light string to a ceiling. Okay, so this is my light string. So that means I'm going to ignore its mass, its negligible mass. So this particle-like bob and the string is stretched by a angular distance theta from the vertical position, and when we release it, it's going to start oscillating on this axis, so it will go back and forth between these maximum points. So it will keep oscillating around this axis so that this angle will be theta. And what I would like to know is, for this oscillation, what will be the period of small angle oscillations. So let me write here what I have. I have a particle mass m. I have a light string, and I see that there's going to be two forces acting on this particle. So let me draw a free body diagram for m. So I'm going to see that I have the weight mg, and then there will be the tension T, which is pointing towards the pivot point. So where is the pivot point? Here I have the pivot point P. And what is the angle between the vertical and the tension force? It's going to be theta. Okay. So I find that the motion is circular, is part of a circular motion. It's a circular arc that I'm drawing, going in between plus theta and minus theta, maximum angular displacements. So I would like to basically say that I have a radial force here and a tangential force. Okay, so this is part of a circular motion. So I have two axes of interest. So there is the radial axis. So that's this axis here. That's the radial axis. And there is the tangential axis, which is perpendicular to it. That is this axis. So this is in the direction of r hat. So that will be r hat, and this will be theta hat, so that I define theta to be increasing in this direction. Okay, and I'm interested in the motion that is forming a circular arc here. Okay, so if I write the net force on the radial axis, what do I have? So I have the angle theta here, the same angle theta. So it is right here. This is the angle theta. So I have tension minus mg cosine theta is equal to mv square over r, where the string length is L. So it is the radius of this circular motion is L, mv square over L. And the tangential force I look at, F theta, it is minus mg sine theta. And what is this equal to? Mass times the tangential acceleration. Now you can see why I have introduced a minus sign here, because theta hat is pointing in this direction. And where did this come from? It comes from the fact that I have defined this angle to be increasing in this direction, right? So my tangential acceleration is minus g sine theta. Now, when I look at a certain angular displacement here, so if I draw this, making a small angular displacement, d theta along this path, so this is going to draw a circular arc, and this is L, so S, the length of the circular arc that I'm drawing is L d theta, right? So if this is my displacement on the tangential axis, then I have the velocity, tangential velocity is ds dt, that is L d theta dt, it will be L omega, and the tangential acceleration I have is dv dt, it will be L d squared theta dt squared, or L d omega dt, which is equal to L alpha. All right. So if I substitute this tangential acceleration into this equation here, I obtain minus g sine theta is equal to L theta double dot. So the equation of motion I obtain, is theta double dot is equal to minus g over L sine theta. Now, simple harmonic motion is described by this equation of motion. X double dot is equal to minus omega square x. And I know how to solve this one. But theta double dot is equal to minus g over L sine theta, and solve for theta as a function of time. This is in general not simple harmonic motion. But if the angle theta is small, okay, so theta is a small angle, small angular displacement, then I want to look at how for small angular displacement. So let me open up the window here and try to figure out how sine theta behaves for small angles. Well, sine theta usually favors expansion. Behavior around theta is equal to 0 is sine 0 plus the derivative of sine with respect to theta is cosine theta evaluated at theta is equal to 0 divided by 1 factorial theta minus 0, and there will be higher order terms. But I find that sine theta, where theta is small, is, to first order approximation, cosine 0 times theta, which is theta. So it's going to be equal to theta. Therefore, I find that for small theta, the equation of motion becomes approximately minus g over L theta. So I recognize that the equation of motion, omega is square root g over L, which is 2 pi divided by the period, then the period would be 2 pi square root L over. So basically I have found the period of small angular oscillation of initiation angle. So if the angle is large, if it's greater than let's say 10 degrees or so, so for small angle we usually mean something less than 10 degrees. You can check this with your calculator. For angles less than 10 degrees, sine theta is almost equal to theta. Then the equation of motion turns into that of simple harmonic motion. X double dot equals minus omega square x. Now, regarding the solution, what is interesting is that the period of small angle oscillations is determined by the gravitational constant g, and actually this makes the simple pendulum a useful device. If you walk with a simple pendulum on a field, and if there is oil under the soil, the value of g is altered a little bit, and you will find variations in the period of small angle oscillations. So that's one way to look for oil. So it's quite an interesting application. Now, having said that, this is not the only way to solve this problem. So I have used the tangential force in order to calculate the equation of motion. The alternative methods, we're going to see one of them in the next video, in physical pendulum. Alternatively, we can use torque, and we can use energy, rotational energy, in order to calculate this equation of motion. So you can try this on your own. You can take the torque with respect to point P, and then you can write torque equals to I alpha in order to calculate the equation of motion, obtain the equation of motion. Or you can look at the change in kinetic energy equals minus the change in potential energy. So you will write mgh, where h is the height it goes up to with an angular displacement theta. This should turn into the rotational kinetic energy 1/2 I omega squared. Or you can use torque equals I alpha in order to calculate the same equation.